We'll get started, and oh dear, what's going on? Okay, oh, that's part of the reason. Turn off that. And so I've posted homework 4, okay? And homework 4 will be due 1 week from Friday, okay? So I know you have homework 3 that you'll turn in on this Friday, and then you have homework 4 due next Friday, okay?
Yeah.
And I know next week is like everybody's midterm week. I do want to. I do want to suggest taking a look at homework 4 because I think it will be helpful in preparing for the midterm. Okay, and I'll talk a little bit more about the midterm exam on Friday. What's that?
This lecture is
So I guess I don't, I'm not. Yeah, we'll say up through today's content, I guess. Okay, so yeah, we have the midterm exam 7th week Monday, and I'll talk about what will be on the exam on Friday. But I will say, if you take a look at homework 4 and you get through the stuff, I think that will be helpful in your midterm preparations and studies, okay? How's homework 3 coming along? I see a lot of good questions and stuff on Piazza, some very good answers by some of our students as well. So, all right, any questions? We're all good? Okay, then today I will talk about the Metropolis Hastings algorithm, which is very similar to the Metropolis algorithm. And let me just kind of, yeah, we'll get into that. Okay, so Metropolis Hastings algorithm again. So it's another MCMC. Markov chain Monte Carlo. All right, and it's very similar to the Metropolis algorithm. Okay, and the difference is that in the Metropolis algorithm, your proposal distribution has to be symmetric, and in the Metropolis Hastings algorithm, it does not need to be symmetric, okay? So very similar to the Metropolis algorithm, except the proposal distribution does not need to be symmetric, okay? So, so in the Metropolis algorithm, okay, we have a proposal distribution Q. Okay, and we said and Q must be symmetric, meaning that the probability of proposing x prime, given that we are at xq, has to equal the probability of proposing x, our current x, if we were at x prime, okay? Okay, and so, you know, examples of symmetric ones are the you know, the coin flip, where we propose theta plus 1 with probability 0.5, and you propose theta minus 1 with probability equal to 0.5. So that's what we used for the island. That's a proposal, symmetric proposal. Also, the normal distribution centered at xk. So so if we are at xk, how do I draw this? Okay, you know, what's the probability of proposing x prime? The probability of proposing x prime is right there. Okay, and if we are centered at x prime, okay, this is supposed to be look similar, and we say, you know, if we're at x prime, what's the probability of proposing xk? And these two values are at basically the same height, right? Okay, so so that's what we have there. That's the Metropolis algorithm. In Metropolis Hastings, which we'll just call MH, Q does not need to be symmetric. Okay, so this property that Q is symmetric is relaxed. Okay, so, you know, you could. So an example could be, you know, you have a biased coin flip. If we're doing kind of like the islands, it would work if you have, you know, even if you don't have a fair coin, if you've got a biased coin flip, you can still do it with the Metropolis Hastings. Or, you know, I don't know, you have some distribution that looks like this, all right? If you're at xk and you know, propose a value, this is, you know, not symmetric, it'll still work, okay? So Metropolis Hastings is very similar to the Metropolis algorithm, except the proposal distribution does not need to be symmetric. That's the only difference. Okay, so let me just kind of write out, you know, the steps for the Metropolis Hastings algorithm. Okay, and so this is kind of for time k equals 1 to big N. Okay, we are going to sample, number 1, sample, I should say propose an xk, or x prime, propose x prime by sampling x prime from Q given your current value, xk, okay? Sampling x prime from proposal distribution Q given your current value xk. All right? And then find the acceptance ratio, which is equal to the minimum of 1 and the probability of x prime divided by the probability of your current x, xk. So this part's from the Metropolis algorithm. And then the Metropolis Hastings part includes this part, which is to take care of the fact that it is not symmetric. So, excuse me. It's the kind of your proposal probability of getting k if you're at x prime divided by the proposal probability of getting x prime if you're at xk. Okay, so that's going to be your acceptance ratio. And then what you do is you sample u from uniform 0, 1. Okay, and then accept or reject. Accept or reject x prime. So if u is less than the ratio, you accept x prime, and that means the next value, xk plus 1, is equal to x prime. And if u is greater than the ratio, you reject the proposed value, x prime, and xk plus 1 is just equal to your current value, xk, x at 10k. All right, so it's very similar to the Metropolis algorithm. The only thing that has changed is our acceptance ratio, which now includes this term that is the ratio of kind of the proposal probabilities. All right, is this okay? All right, and so I wanted to kind of spend the rest of today's lecture kind of, I don't know, prove probably isn't the right word, but to try to at least show that by setting up our transition probabilities this way, our Markov chain will converge to our stationary distribution, and that stationary distribution will equal the target distribution. Okay, so this is kind of to show that this algorithm does indeed work. Okay, so I want to show that by setting up our transition probabilities according to the Metropolis Hastings algorithm, our stationary distribution of the Markov chain will be the target distribution. Right? Right. And so, kind of from ergodic theory, we have that the Markov chain being aperiodic and irreducible will converge to its stationary distribution given enough time, right? So that our aperiodic irreducible Markov chain will converge to its stationary distribution. So what we need to show is that the stationary distribution is the target distribution, okay? That the stationary distribution equals the target distribution. All right, and and we will say that the stationary distribution is achieved when we have detailed balance. Okay. Okay, and so detailed balance is pretty much the idea that the total probability, or the number, the total probability of going from one state to another state is equal to the total probability of going from that state to this state, right? So we had detailed balance in the island example when the number of people going from island 4 to island 3 is equal to the number of people coming from island 3 to island 4, okay? Or the probability that someone is going from island 4 to island 3 is equal to the probability that someone is going from island 3 to island 4. If that's achieved for all the states, for every possibility, then we have detailed balance, okay? So, we need to show, so we'll say we have transition probability okay, and this will be the probability of transitioning from xk to xk plus 1. Okay, so that's the transition probability. And we have detailed balance. And I'm going to put this on the next slide. We have detailed balance when so we have detailed balance when the this is basically transition probability from xk going to xk plus 1 times the probability of being in xk in that state is equal to the transition probability from xk plus 1 to xk times the probability of being in xk plus 1. Okay, so we will have detailed balance of this when this happens. Okay. All right, and so we got to figure out, you know, how does this happen? Okay. So our so in the Metropolis Hastings algorithm, okay, there are two possibilities, okay, for a proposed value x prime, okay? One is we reject x prime, and in that case, xk plus 1 is equal to our current value xk. And two is we accept x prime, and then xk plus 1 is equal to x prime, and which is different from xk. Right. So in the case that we reject x prime, the detailed balance thing is trivial because xk plus 1 is equal to xk. So I'll just kind of show this. All right. So you know, we have detailed balance. Oops. When this happens, okay. So in the case where we reject the proposed value x prime, we have detailed balance, okay, because x at time k plus 1 is equal to x at time k. So, you know, so x at time k plus 1, you know, this just reduces to xk plus 1 is equal to xk. So, you know, it's the transition probability of going from xk to xk times the probability of being at xk, and, you know, xk plus 1 is xk times the probability of being at xk, right? So the detailed, you know, at this point it's trivial because these are just people who are basically staying at the island one more time, right? So is the probability, is the number of people who you know, stay at the island same as the number of people who stay at the island? Yes, okay, this is kind of trivial. So we really just need to show that we just need to show we still have detailed balance when xk plus 1 does not equal xk, all right? So when the next state is different. Okay, so let's take a look. All right. So the transition probability of going to xk plus 1, given that we are at xk, is equal. So first we've got to propose, well, let me, I'll write it this way, okay? Is equal to kind of the probability of accepting it times our acceptance ratio Okay, so this is the probability of transitioning from xk to xk plus 1 is equal to basically the probability of accepting the proposed value times the probability of proposing that value in the first place. Okay. Does that make sense? So the probability that a random person or thing is transitioning from xk to xk plus 1 from one state to another is the probability of kind of accepting that proposed value times the probability of proposing that value in the first place, which is what we have here. We've got q, this is the probability of proposing the value times the probability of accepting it, okay? I'm going to rewrite this 1 to be let this be the probability of xk divided by the probability of xk. Is that all right? So instead of 1, I'm going to write it as p of xk divided by p of xk. Okay, and then so if I do that, then let's kind of distribute out this thing. So we've got t of xk plus 1 given xk is going to be equal to the minimum of probability of xk over probability of xk times q of xk plus 1 divided by, not divided, given xk, right? Huh? Did I mess something up? So I'm just distributing this multiplication over the minimum function, okay? And then over here, I've got probability of xk plus 1 divided by probability of xk times, and then this thing will cancel, and I've got q xk given xk plus 1. Is that okay? The math step that I've done. All right, and then I'm going to pull out a 1 over p times xk times the minimum of probability of xk times q xk plus 1 given xk and probability of xk plus 1 times q of xk given xk plus 1. All right, let me just verify with my notes, just because there's so many k's and k plus 1s, it's easy to make a little mistake. So I got 1 over p of xk minimum p xk, xk plus 1 given xk, p xk plus 1, q xk given xk plus 1. Okay, so this looks good to me. All right, if we follow the same logic, but for the other transition, okay, so if I do, so using kind of the same logic and reasoning, and I'm going to kind of skip it if that's okay, logic and reasoning, if we do the transition probability of going from xk plus 1 to xk, all right? Effectively, I'm just switching symbols here. So I've got transition from, B to, going from A to B. if I switch them and say, you know, what's the transition probability of going from B to A or something like that, and I just kind of switch the letters, I can just switch the symbols that we have here, right? Or, you know, you could follow the process and do the exact same thing, and you're going to get 1 over probability xk plus 1 times, so this one up here is transition of, so I'm just switching the letters, okay, and I've got, or switching symbols. So wherever I see a xk plus 1, I'm going to switch to xk, and wherever I see xk, I'm going to switch to xk plus 1, okay? Okay. Now we could go through the exact same steps that we had before and arrive at the same thing, but I'm kind of just shortcutting that. Is that all right? Nobody's going to argue with me here? All right, so let me just kind of copy these over. So we have the transition probabilities. We have the transition probability of going from xk to xk plus 1, and we have the transition probability of going from xk plus 1 to xk, right? I'm going to just copy that. So this is, you don't have to rewrite it. I'm just putting it up there so we have it for reference here. Okay, so, you know, we have detailed balance. When Tx, the probability of going from xk to xk plus 1, given that we are at xk, if that's equal of, you know, going the other way, of going to xk if we're at xk plus 1 times the probability of being at xk plus 1, right? So we'll have detailed balance when we have that. So let's just see what we have. Okay, so T of xk plus 1 given xk times the probability of xk. This will equal the probability of xk, and I'm going to just copy and paste my transition probability that we figured out in the previous slide. All right, so I'm going to just copy and paste that right here. Is that okay? So, so this will cancel with this, and the total kind of transition probability of transitioning times the probability of being there is going to be the minimum of this function, right? And then, on the other hand, the probability of going the other way, going to xk if we are at k plus 1, multiplied by the probability of being at xk plus 1, this is going to equal probability of xk plus 1 times our transition probability, okay? So I need to copy this. Okay, and so this term will cancel with this term. Okay, and then if we, so we're just left with this minimization term, or not minimization, but just the minimum term between these values, and we see that this thing is exactly this term right here. So these two are equal. And then this term over here is exactly equal to this term. Okay, so the basically the probability that one is going to the other is going to be the minimum of the same two terms. Okay, so you have the same two terms, which is so the minimum of the same two terms is going to be the same for both, right? So the two terms are equal. So the two terms are indeed equal, which says is this the terminal one? I don't know. Excuse me. All right. So we do have, so this times probability of xk is indeed equal to the number going the other way, or the probability going the other way. Okay, so we have detailed balance. Right. So if we set up our transition probabilities according to the Metropolis Hastings algorithm, then we will have detailed balance when the target distribution is kind of the probability of each of our states. Okay, because this is our transition probabilities, which is set up according to the Metropolis Hastings algorithm, and this is when we will have detailed balance, when the states have this probability, and this is the probability that is our target distribution. Okay, and then and if it holds for the Metropolis Hastings algorithm, then it will hold for the Metropolis algorithm, because the Metropolis algorithm is just a special case of the Metropolis Hastings algorithm where your proposal distribution is symmetric. Okay, and that's basically it. Okay, so I guess I can just write that. So we have detailed balance when the probabilities of our states follow the target distribution. Okay, and then if we have detailed balance for the Metropolis Hastings algorithm, we also have it for the Metropolis algorithm. Okay, because the Metropolis algorithm is just a special case Metropolis Hastings where Q is symmetric. Okay, are there any questions? I flip back. All this works out okay. So setting up our transition probabilities according to the Metropolis Hastings algorithm gives us these transition probabilities, which will achieve detailed balance, and that basically means that if we let the Markov chain run long enough, it will converge to its stationary distribution, and the stationary distribution is our target distribution, which is exactly what we want. Okay. All right, we'll end there, and we'll see you guys on Friday. On Friday, I'll talk about the midterm exam that's coming up, and we'll see you then.